All right, let's jump right into this explainer. Picture this. You're at a massive enterprise project. You know Power BI like the back of your hand. You're building incredible dashboards, writing solid DAX. But then you have to connect that beautiful front end to a scattered, fragmented back-end data ecosystem. Yeah, that's where things get super messy. So today, we're demystifying Microsoft Fabric. We're going to break down its architecture, its compute engines, and its analytics layers step by step to show you exactly how it solves this massive headache.
Because let's be real, fragmented data platforms are the ultimate pain point, aren't they? You've got your data warehouse over here, your data lake way over there, Spark notebooks running somewhere else entirely, and Power BI is just trying to pull the whole shebang together. It is literally exhausting just to maintain all those connections. Well, Fabric is Microsoft's answer to this. It's a unified, single-platform SaaS environment. In this explainer, we're going to build this architecture layer by layer so you can see exactly how it all seamlessly fits together.
Okay, let's dive into this. Looking at this Microsoft Fabric career roadmap, you really get a sense of just how vast this ecosystem is. It spans data engineering, analytics engineering, BI dev, and even AI. Listen, if you're a data engineer, or especially if you're gearing up for those DP-600 or DP-700 certifications, consider this explainer your ultimate bridge. We're taking the pure theory and connecting it straight to the real-world architectural decisions you're actually going to make out there.
So, here's our architectural journey for today. First, the Fabric Challenge. Then, the OneLake Foundation. Third, Lakehouse versus Warehouse. Fourth, Direct Lake and Models. And finally, Performance and Capacity.
All right, kicking things off with Section 1, the Fabric Challenge and Ecosystem Integration.
And this brilliantly illustrates the overarching architecture. Notice how your external data sources, whether they're chilling in Amazon S3, Azure Data Lake Storage Gen 2, or Google Cloud Storage, they don't actually need to be moved. No way! They connect via shortcuts straight into OneLake. From there, this single storage layer feeds directly into a multi-engine compute layer. So whether you're using SQL Data Warehouse, Synapse Spark, or Power BI analysis services, they are all crunching the exact same underlying data. It's a massive paradigm shift.
Moving on to Section 2, the OneLake Foundation, our unified SaaS storage.
So the absolutely crucial point here is understanding what OneLake actually is. Basically, think of it as the OneDrive for data. It provisions automatically with your tenant, built right on top of ADLS Gen 2. But it's really built on three core pillars. First up, the single copy concept. Your data is stored exactly once in an open-source Delta Parquet format, meaning no compute engine has to copy or transform it just to read it. Huge time saver. Second, it uses those shortcuts we mentioned to create a distributed data mesh without physically moving a single byte. And third, the whole thing is fully SaaS integrated. There's zero infrastructure for you to spin up or manage. None.
Now, because OneLake spans your entire organization governance as well, it's critical. If you're tackling that DP-600 exam, definitely pay close attention to this workspace strategy. You really want to group your workspaces into logical domains and subdomains, stuff like finance or operations. You should always separate workspaces by environment. I'm talking dedicated dev, test, and prod spaces. You've also got to separate them by domain and team boundaries so data ownership is crystal clear. And again, always leverage those shortcuts instead of copying data between workspaces.
So within those workspaces, you're going to create lakehouses. And a Fabric lakehouse has a really specific architecture, split into two distinct zones. Up top, you have the files area. This is your unmanaged landing zone, basically where you dump your raw CSVs, JSONs, or any unstructured data. Spark can read it, sure, but it doesn't have a relational schema yet. Down on the bottom, you have the tables area. Once you run your Spark ETL process, the data gets written down here as managed Delta Parquet tables. And here's the real magic. Any table created here is instantly registered in the Fabric Metastore, and boom, it's queryable via SQL.
To manage that whole flow from files to tables, we use the Medallion Architecture. This is pretty much the industry gold standard for data curation. You start at the bronze layer. This holds your raw history exactly as it landed, usually just simple appended files. Next, the data flows to the silver layer. This is where you clean, deduplicate, and schema validate your data, storing it as Delta tables using upsert or merge operations. Finally, we hit the gold layer. This data is highly aggregated, beautifully curated, and modeled into a tight star schema specifically for your BI reports.
All right, Section 3, Lakehouse versus Warehouse, and choosing the right engine.
Now, what's really interesting about this setup is the auto metadata sync.
Every single time you create a lakehouse in Fabric, the system automatically provisions a read-only SQL Analytics endpoint. What does that mean for you? It means your data engineers can be writing data using Spark notebooks in the Lakehouse, while your SQL analysts are simultaneously querying those exact same Delta tables using standard T-SQL. No data movement, no manual configuration, it just works.
But this does bring us to a pretty major architectural decision. Should you use the Lakehouse or the fully fledged Fabric data warehouse? Let's frame it like this. If you're a data or Spark engineer, you want the Lakehouse. The SQL endpoint there is strictly read-only via SQL. All your actual write operations have to go through Spark or pipelines. However, if you're a traditional SQL or relational developer, someone who relies heavily on insert, update, and delete statements, you definitely want the Fabric data warehouse. It uses the Polaris engine for full read and write capabilities with standard T-SQL, and it fully supports multi-table ACID transactions.
Moving into Section 4, Direct Lake and Models, where we get into high-speed analytics. So how do we get data to the business user at lightning speed? The answer is Direct Lake mode. It's honestly a path-breaking technology. Instead of importing data into memory or translating queries to SQL, which, as we know, causes latency, Power BI Analysis Services pages the column arrays directly from the Delta Parquet files in OneLake, straight into RAM. Walking through the sequence here, that fast path is absolutely incredible. But notice that crucial step at the bottom. If memory limits are exceeded or certain rules get broken, it triggers what's called a silent fallback. Power BI is forced to drop back to standard direct query mode, which generates a T-SQL query that hits the SQL endpoint instead. The result? That visual that used to load in 50 milliseconds suddenly takes 3 whole seconds to load. Ouch.
To keep your reports humming at maximum speed, you have got to avoid triggering that fallback. And there are a few very specific triggers you need to watch out for. Exceeding your capacity limit? That's one. Schema changes happening behind the scenes without updating the semantic model? That's another. Using SQL views instead of physical Delta tables will also do it. But honestly, the most common trap is security. If you define row-level security or object-level security at the database level, like in the warehouse or SQL endpoint, Direct Lake literally cannot read the files. You absolutely must define RLS and OLS directly inside the Power BI semantic model using DAX if you want to keep things fast.
Semantic model design is super critical here too. If you want Direct Lake to perform flawlessly, you have to stick to strict enterprise star schema rules. Focus purely on central fact tables surrounded by dimension tables. Use one-to-many relationships. Enforce a single cross-filter direction where dimensions filter facts. Whatever you do, avoid bidirectional filters and those complex snowflake schemas. They create these incredibly messy join paths that will completely overwhelm analysis services, exhaust your memory arrays, and pretty much guarantee a fallback to direct query.
Beyond just the shape of your schema, there are 3 specific optimization steps you really should take to minimize your model's memory footprint and stay under your capacity limits. Step 1. Disable auto date/time in Power BI. Leaving that on generates hidden date tables for every single datetime column, which wastes a massive amount of memory. Step 2. Reduce your column cardinality. Basically, don't bring in highly unique text columns like GUIDs or raw timestamps unless you absolutely have to. Step 3. Optimize your data types. For instance, cast high-precision floats down to fixed decimals or integers. The engine compresses integers way better than floats.
And finally, Section 5, Performance and Capacity. Managing the life cycle of your architecture.
Let's move to and see how this builds into capacity management. Fabric runs on allocated capacity units, like an F64 tier, for example. Now, because queries and pipelines can be totally unpredictable, Fabric uses a smoothing and throttling algorithm. Instead of just crashing your system when a huge query hits, Fabric averages your capacity consumption over a window of time. If you consistently blow past your limit, even after this smoothing process, that's when the throttling engine kicks in. And here is the major takeaway. It protects your background pipeline jobs, but it will progressively delay and throttle your interactive operations first. Meaning your actual users will experience slow report loading way before your data factory jobs ever fail.
Part of managing that performance comes down to how data is written to disk. And hey, if you're taking the DP-600 exam, you are basically guaranteed to be tested on the difference between V-order and Z-order. So let's clear it up.
vOrder is a proprietary write optimization built specifically into Fabric. It rearranges data inside Parquet files to enable lightning-fast sorting and filtering, specifically for the Power BI Analysis Services engine. And it's enabled by default. zOrder, on the other hand, is an open-source multi-dimensional clustering technique used by Spark and SQL engines to skip scanning irrelevant data. The cool part? They actually complement each other, and you can totally use both on the exact same table.
So as you can see, Microsoft Fabric fundamentally changes how we think about data silos. It completely moves us from a world of fragmented storage into a unified, high-speed compute mesh. The real question is your enterprise ready to make the shift? If you found this useful, visit datastable.com for more Microsoft Fabric, Power BI, Azure, and data engineering tutorials.